Hello and welcome to lesson 5.2. So this is a piece of chapter 5, and chapter 5 I told you last time was all about polynomials. And we started with adding and subtracting polynomials. Well, the natural place to go next would be to multiplying and dividing polynomials. But before we can do that, we need a little bit of skills in something called exponents, exponent rules, and then we'll be able to mosey into the rest of our chapter of dealing with polynomials. So, uh, good question maybe to start with is, what is an exponent? Well, it's quite simple. A lot of people like to make this harder than it is, but if I were to give you something like x to the fourth, all an exponent is a count of how many of these x's I have multiplied out by itself. So x to the fourth means I have 4 x's all multiplied together. So this is what's called expanding out the exponent. We'll do this a lot to discover exponent rules so that if you ever forget them, you could easily think through or rediscover them yourself. A little bit of terminology before we begin. Um, if I happen to have something written out in exponent form, this thing down here on the bottom is called the base, and the little number floating up top, that's the exponent. Okay? The only reason I need to let you know that is I'll use words like base and exponent in today's lesson. I won't test you on definitions like that, but you need to know what I mean when I say, hey, look, do these things have the same bases or like bases? Okay, so what I'm going to do is there's a bunch of exponent rules or exponent, yeah, let's just call them exponent rules that we need to know to be able to kind of simplify things or to be able to work with exponents. And so I'm going to just go through and we'll look at all these. Now, these are not like official rule names or anything like that. Different textbooks will call these rules different things, and the order I'm teaching them in is just the order that makes the most sense to me. You could teach these, so rule number 1 is not necessarily rule number 1 everywhere, but a lot of textbooks will call this multiplying like bases. Multiplying like bases. And it's a good place to start. What that means is if I have two exponents, like x squared, or two expressions with exponents, and they're being multiplied, x squared times x to the fourth, I would like to have some sort of rule to be able to simplify this. Because what I'm going to want to do is to be able to write things in a simple, neat, succinct form as possible. So how do I go about simplifying this? What's the rule for multiplying like bases? Well, here's what's really fun. I know how to expand out x squared. I know how to expand out x to the fourth. So let's do that to see if we can explore the rule without me just telling you, okay? So x to the second power, x squared, that is just 2x's, x times x. Okay, you agree to have written down x squared right there. It's times x to the fourth, which is just 4x's. And when I look at this, 1, 2, 1, 2, 3, 4, wait a second, I just happen to have 6 x's all multiplied. And knowing that I could go the other way with expanding, I could put this back together. This would just be x to the 6. I have 6 x's all multiplied. I could write this really succinctly as x to the 6. Oh, wait a second. With this expansion, this is just us discovering the rule. You don't have to do this. I think I can see the rule or a shortcut for doing this. What if I were to just instead say, wait a second, I know x squared means I have 2 of these x's, x to the fourth means I have 4. What if I were to just add the exponents together? 2 plus 4, that would be x to the 6th. Oh, well that's the rule. If you have like bases and you're multiplying them, all you have to do is combine them into a single base and add the exponents. So we should be able to do this kind of quickly and easily. Something like x to the 5th times x to the 3rd. Oh, well that's just going to be x to the 5 plus 3, which is x to the 8th. I'm not going to require you to show this step, so a lot of people will be able to just do 5 plus 3 in their heads and will be able to jump right to the correct answer and say, oh yeah, x to the 5th times x to the 3rd, that would be x to the 5 plus 3 is 8. So that's pretty quick and simple. Now, things you should know, I could expand this out as far as I want. What I mean by that is I could ask you something like x squared times x to the fifth times x to the third. I could go for as many of these bases being multiplied together. As long as they are the same base, I can combine things into a single base. And I would have 2 plus 5 plus 7 as the exponent. Sorry, 2 plus 5 plus 3. 2 plus 5 is 7. 7 plus 3 is 10. So x to the 10. Okay? So I could do 100 bases multiplied together as long as they're like. What if they're not like? What if we go with like x to the third times y to the fourth times x squared? Well, I look at this and I say, hey, this y term, it's not like this x term. They're different bases. So I cannot combine these two together into a single base. But wait a second, I see an x base here and an x base there. I'd love to get them together. Well, because it's multiplication, I could rearrange this in any order I want because multiplication is commutative and associative. So that means that I could regroup, I could rearrange, as long as I'm not moving anything across other operations right now. These are all being multiplied. I could rearrange this, so I could put these beside each other. Now, I typically don't take the time to show that. Most people would just jump to this answer and say, oh, I have a like base here, like base here. 3 plus 2 is 5, x to the fifth. Y to the fourth doesn't have a like base, so it stays y to the fourth. But I am allowed to rearrange because this is just multiplication if it makes you feel better, because multiplication is commutative and associative. Okay? So if you want this second step here, you can do it, but just know that you are fine and okay to jump from the red to the blue. All right? Well, that wasn't too hard of a rule. Let's look at the second rule. The second rule, if we did multiplying like bases, the second rule is naturally to divide like bases. And we'll see if we can discover the rule as well instead of just telling you. And so let's start with something simple to discover the rule. X to the fifth divided by x squared. So this is the same base on top of this fraction and the same base on the bottom being divided here. And so let's see, let's expand these out. That's the way to discover these rules. X to the fifth would just be 5x's multiplied. So 1, 2, 3, 4, 5. I can't count, so I got to be careful. And x squared is x times x. Okay, well this looks kind of weird, but 1x on top will divide away to 1 or cancel out with 1x on the bottom. So I could start striking these out. This x divided by this x will give me 1 and be gone. This x divided by this x will give me 1 and be gone. And what I'll be left with is just 3x's up top, or x to the third. And you could write it this way for a second, but we don't need to leave that. We could go ahead and switch it to just plain x to the third. What would be the rule to go from this to this without having to do all that exploring work? Oh, well, the rule is quite simple. The rule is take the top exponent and subtract the bottom exponent. And we're going to write this on top of the fraction. Don't need anything down there on the bottom right now. And 5 minus 2 would be x to the third. That makes sense. If multiplying, the rule was to add the exponents, dividing, the rules to subtract the exponents. Okay, and we could do more things. Now, the important piece here is to always just do this with the bases. So if I have another thing, like a 5 floating there, leave the 5 alone. Let's do that. So a lot of people struggle with this, not just because of the 5, but you look at this and there's no exponent there. Well, this is just like when we add 1s out front or below. I can always put an exponent of 1 if there's no exponent showing. And so now I should be able to handle this problem. The 5 is not going to move. It's just going to stay there. It's not part of the x's here. And so the x's will be x to the 7 minus 1. or 5x to the 6th. Okay. Now, I want to give you one that we're not going to finish now until we get another rule, but one that I want to make you think something about. X to the 3rd over x to the 7th. If we go to try to do this one, those are the same bases, so I can combine them into a single base. And the top exponent minus the bottom one, 3 minus 7. That would be x to the negative 4. But what in the world does that mean? If the exponent's telling you how many x's you have, how can I have negative 4x's being multiplied? That doesn't make sense. Well, I'll go ahead and tell you this is not proper or not all the way simplified. We're not allowed negative exponents. Okay? They are not allowed at all. So we'll have to figure out a way how to fix it, okay? We'll need to be able to fix it, and that'll be one of our exponent rules. Actually, it's our next exponent rule, okay? So let's kind of continue on with this one. We'll continue fixing this one. So rule number 3, it's fixing negative exponents. They are not allowed. So if we go back to this example where we had x to the 3rd over x to the 7th, and you worked beautifully. You said 3 minus 7 is negative 4. How are we going to fix this? What does this even mean? Well, I think to figure this out, it'd be good to go back to the original and expand it out. So let's do some scratch work or scratch thinking over here. X to the 3rd over x to the 7th. And so up top I have 3 x's being multiplied, and on the bottom I have 7. Had to concentrate to count those. Now what's going to happen is if I have one on top and one on bottom, they can divide out to 1 and be gone or cancel. One on top, one on bottom, one on top, one on bottom. So these 3 up here cancel out with these 3 on the bottom. What am I left with? I don't have anything left up top, and I have 4 x's, or x to the 4th, on the bottom of the fraction. Now I can't leave a fraction like this naked up top, so I got to put a 1 to hold the spot there. This is just like the sign you see in all the stores, the no shoot, no shoes, no shirt, no service. They never mention pants. You don't have to put pants on, but you definitely have to put a shirt on. And so if you have a fraction that's naked up top, put a shirt on it, put a 1 up there. But wait a second, what does this mean then? X to the negative 4th, is that equal to 1 over x to the 4th? Because this is x to the 3rd over x to the 7, it's equal to this. This is x to the 3rd over x to the 7 is equal to this, and the answer is yes. These are in fact the same things. So how do I fix a negative exponent? Wherever it is, whether it's in the top of the fraction or the bottom of the fraction, you grab the base, you grab the exponent, and you move it to the other side. So there's no fraction here, so it's understood to be over 1. And so this is in the top of the fraction. So to fix this, I grab it and put it on the bottom of the fraction. And what happens is every time you move a base and its exponent up or down, and you can move it up and down as many times as you want, it turns on and off the negative sign on the exponent. It does not mess with negative signs out front, just on the exponent. So if I take a base and its exponent and move it down or move it up, it changes the sign. Now I need a shirt on this. So 1 over x to the 4th. Once again, we only move things that have, we only want to move things that have a negative exponent. We can move anything we wanted to, but it's important to fix that because that's part of being proper and finished simplifying. So let me give you some examples. Let's do something like this. 2 over x to the negative 5. Okay, we look at this and we say, oh man, we're not allowed negative exponents. We need to fix it. Now, let me ask you a question here. Does this 2 have a negative exponent? The answer is no. The exponent on this 2, it's its own base. The exponent on this 2 is a 1. So this 2 is not going to move. It's going to stay on the top of the fraction. Now, this x has a negative exponent. It is on the bottom of the fraction, so to fix it, it needs to move to the other side of the fraction. If it's on the bottom, the other side is the top. So this x to the 5th is going to move up to the top, And whenever you move this up or down, the little negative sign turns on and off. So this will become a positive x to the positive 5. Now, I moved everything out the bottom of the fraction, but I don't have to worry about putting pants on it. I only need to worry about shirts, because just like the sign at the store says, no shoes, no shirt, no service, never mentions pants. So there, so I simplified that. I fixed it by getting this x to the negative 5 up to the top of the fraction. The 2 got to stay put because it wasn't negative. It wasn't bad. Let's do another example. What if I were to do 5m to the negative 3? And we look at this. Let me ask you, does this 5 have a negative exponent? And the answer is no, it has an exponent of 1. This negative 3 is only applying to the m. So does the 5 have to move? No, the 5 can stay right where it is. There's no fraction here, so this means this is the top of the fraction. If you wanted to put a 1 on the bottom, you could to let yourself see that. So this m to the negative 3 needs to move. If it's on the top, it will move to the bottom. And whenever you move something, it turns on and off the negative sign on the exponent. So there, we can fix negative exponents really simply. Let me give you one more example and I'll move on to the next rule. What about something like this, like 2x to the 4th y to the negative 3? Okay, well, we look at this. Notice I have, in this one problem, 3 different bases. I have a 2, an x, and a y. Which of them has a negative exponent? Only the y term. So that means nothing else is going to move. 2x to the 4th is going to stay right where it is because the 2 has a 1, positive 1, and the x has a positive 4. They don't have to move. The y to the negative 3 has to move. Notice there's no fraction shown, so this is understood to be the top of the fraction, so I need to move this y to the 3rd to the bottom of the fraction. And whenever I move a base and its exponent top, up, or down, what I have done is turned on or off the negative sign on the exponent. Okay? So while that's a rule that a lot of people don't like, it takes them a while to grasp it fully. It's not that hard of a rule. You're just rewriting something either in the top or the bottom of the fraction and getting rid of the negative. Okay? Let's keep moseying with a few more rules. Rule number, I think we're up to 4. It's the 0th power. 0 power. I guess I could put a th on the end of that. So that's whenever we raise anything. I'll go ahead and write the rule for you. Anything to the 0th power. Guess what that equals? A lot of people get this wrong. Anything to the 0th power equals 1. For instance, 5 to the 0th power. Go ahead, what's that going to be? That's going to be 1. Negative 3, let's put it in parentheses. We'll talk about that in a second. To the 0th power, hey, that's 1. X to the 0th power, you guessed it, it's 1. What if I go with something as nasty as I can think up, like 2075x plus the square root of pi, I don't know, minus the normal distribution, which is a capital Greek letter, divided by 5. If we put that in parentheses and raise it all to the 0th power, guess what it equals? 1. Anything to the 0th power equals 1. Why? That feels weird. Well, I'll show you why. So let's kind of work this from something. Let's start with it doesn't really matter what I start with. Let's start with x to the 5th over x to the 5th. Okay. And if I wanted to do my exponent rule, we would know that I take the top exponent and subtract the bottom exponent. X to the 5 minus 5, well, that's x to the 0th power, right? But wait a second. If I have a fraction with the same thing on top and same thing on bottom, those things are going to cancel or divide out and leave me with nothing but 1. For instance, if I had 3 divided by 3, or x divided by x, or x squared divided by x squared. If I have the same thing on top and bottom, that divides to 1. So x to the 5th over x to the 5th is equal to 1. But if I wanted to use exponent rules, it's equal to x to the 0. So anything with x to the 0th power is equal to 1 because the step before it reached the 0th power is like having the same thing on top and bottom of the fraction. Like 5 to the 0th power, that's like having 5 to the 1st over 5 to the 1st. or 5 squared over 5 squared, or something like that. Okay? So this is one that a lot of people just memorize. They say, okay, anything to the 0th power is equal to 1. Okay? Now my next rule is not really a rule, but we'll call it rule number, I think we're up to 5. I'm just going to say, be careful with parentheses. Okay, so here's the general rule for an exponent. It applies to whatever it is directly touching. So let's do one that's a hot topic, kind of topic of hot debate. Is there a difference in negative 5 squared versus negative 5 in parentheses squared? And the answer is yes. While we mostly mean these to mean the same thing when we say them, they drastically mean something different. The exponent only applies to what it's touching. So in this case, the 2 is touching the 5, not the negative sign. This negative sign is just like a negative 1 floating out front. And we have a 5 squared. So negative and 5 squared would be 5 times 5. So this would be negative 25. Over here, the exponent's touching a grouping symbol. I can't have half of a parenthesis. The 2 is touching this parenthesis, so that means it is grouping or squaring everything in this parenthesis. So what it means is, what do I have 2 of? I have 2 of these parenthesis groups. And what happens to be in these parentheses is negative 5. And a negative times a negative is a positive, and 5 times 5 is 25. So often when we say negative 5 squared, this is the one we mean. This one is not the one we typically mean when we're speaking. Now, if you don't believe me, put those in your calculator, and you will see that you get negative 25 for one of them and positive 25 for the other. This is all because exponents apply to directly what they're touching. So this 2 is only applying to this 5. This 2, the square, is only applying to this parenthesis, which happens to group this entire thing. Okay? So we can have more fun with this. We can do things like, hey, there's got to be a difference of negative 3 to the 0th power versus negative 3 to the 0th power. I'll go ahead and do the easy one first. Negative 3 to the 0th power in parentheses. This 0 is touching this parentheses, so the entire thing is 1. Here, what is the 0 touching? Just the 3. This negative sign is floating out front, kind of like a negative 1 times 3 to the 0th power. Anytime the exponent doesn't have parentheses, you need to separate out things that are in front of it like this. And so negative 1 times 3 to the 0th power is 1. So this one ends up being negative 1. Once again, if you don't believe me, check it in a calculator. One more example just like this, and we could do hundreds of examples, but just be careful with this, things with parentheses. What about something like this? 4x to the 0th power versus parenthesis 4x to the 0th power. Everything changes with and without parentheses. With parentheses, the 0 is touching the entire thing because it's touching the parenthesis, and that's a grouping symbol, grouping it all. And you know anything to the 0th power is 1. Over here, the 0 is only touching the x. The 4 is just out there. This is 4 times x to the 0th power. Well, what is x to the 0th power? You know that's 1. What's 4 times 1? That's 4. These are drastically different. Okay? So just be careful with and without parentheses. Often whenever we're talking, anytime we mention things, we mean parentheses. When I tell you, hey, find negative 5 squared. Typically what I mean is negative 5, all of it squared, so I need grouping symbols. Or if I say, hey, 4 times x to the 0th power, I typically mean I want all of it. So there's a difference. In English, we don't really have a way of wording it differently in our mouths when we speak, but we write it differently when we mean different things. So be careful with that. I will say that this is something that they like to do sometimes on the test. It's kind of little tricks like this question. They love to give 4x to the 0th power, knowing that you'll just jump to 1. If there's no parentheses there, though, it's 4. Okay? I'm trying to think. I think I had one more thing I wanted to say here, but I've forgotten it. So I'll just mosey on to the next rule. Last rule. Okay. If it comes back to me, I'll come back here and talk about it. Last rule. I believe we're up to like rule number 6 or something like that. And this one's called, some places call it a power to a power. Okay, and this is what we mean. Let's say I have x squared in parentheses raised to the 5th power. Okay? How am I going to handle this? Well, let's do the same thing we've been doing to explore. Let's expand this out, but I got 2 sets of exponents to expand out. Let's first start with the outside one. 5 is touching this parentheses, so that means I have 5 sets of these parentheses being multiplied. I think that's 5. 1, 2, 3, 4, 5. Okay. And what's inside each set of parentheses is an x squared. Now let's expand out each x squared. Well, x squared just means x times x. Whew, it's taking a long time to write. Should have used smaller numbers. All right, well, you look at this, all I have is multiplication of a bunch of x's, so the parentheses are not needed. If you were to write them all out, I believe that should be 10 x's, because I have 5 groups of 2. So you could have 10 x's all written out, but I know a lot shorter way of writing that. That's x to the 10th. Ooh, I think I just discovered the rule to shortcut all this work. The rule is when you have a exponent on the inside with an exponent on the outside, you multiply them. So that would be x to the, and I'm going to show the step. Remember, you don't have to show this step. 2 times 5, or x to the 10. Okay? Now, I will caution you on all of these exponent rules. If you go back and look at every example that we've done today, every exponent rule only applies when we're talking about a single term at a time. You do not see any pluses or subtractions in this parenthesis set. You do not see any pluses or subtractions in any of these things. This one's different because the parenthesis is grouping everything. Here, I'm not trying to combine exponents across plus signs or subtraction signs. It's just divisions. And here, just multiplications. Notice there's no pluses or minuses in between any of the bases. So exponent rules cannot reach across plus and minus signs. They only apply to single terms at a time, or 2 terms being multiplied, or 2 terms being divided. Okay? Let's do 1 or 2 more examples of this power to a power rule. Maybe one with a coefficient, so we could be kind of understand, or, see that and be careful with it. So something like this. Let's go parenthesis 2x to the 3rd, and let's raise it to the 3rd power. And so a very important question for me to ask you is, how many bases do you see inside this set of parentheses? And the answer is there are actually 2 bases, the x and the 2. There's no exponent written here, so I can add a 1. So whenever I do this, it's not just to a single base, I can do it to multiple bases. Every exponent inside the parentheses here will be multiplied by 3. So I will get 2 to the 1 times 3 is 3, and x to the 3 times 3 is 9. Okay, now most of you might know that 2 to the 3rd is 8, but I'm perfectly okay if you just leave that as 2 to the 3rd. We're just practicing exponent rules, not practicing your calculator skills. I'm okay with either answer, but I'm going to just leave it there. Let's do one more of these before we mosey on. So something like 3x squared divided by y to the 3rd. We'll put it in parentheses, and let's say the exponent is 2. Okay, so looking at this, there are 3 bases inside this thing. This rule reaches across divisions as well. Okay, so I can put an exponent on this 3 so that we notice that 3 is a base, x is a base, and y is a base. And all of those exponents on these bases is going to be multiplied by 2. So 1 times 2 is 2. X to the 2 times 2 is 4. And y to the 3 times 2 is 6. Beautiful. So those are all the exponent rules. Now we have one last thing I'd like to do with you, and that is, this is kind of getting to be a long lesson, I'm sorry, I apologize, but that is, can we put it all together? Can we combine all these exponent rules to simplify? So when simplifying using exponent rules, a lot of people, I got good news and bad news. And I think it's the same bit of news. There is no proper order to apply an exponent rules. We can do this in a lot of different orders. You may do it differently than I do it. We both may do it differently than someone else in our class. So the order actually doesn't matter. We can just apply exponent rules until we're simplified. What does it mean to be simplified? What we have here is we have combined all like bases. It's kind of three things we want to achieve. We want all like bases combined with whatever rules required. We want no parentheses left. We want to use up all of them. Use up all of the parentheses. And then, of course, there's no negative exponents allowed. So fix all negative exponents. If we've done those three things, not necessarily in that order, in any order, however you want to achieve this, then we are simplified. Okay? So, let's jump into some examples. Let's start with something simple, like 5 to the negative third over 5 to the negative 5. So there are so many different exponent rules you could do to do this. There's no proper order. Once you get used to these, you can be a little bit faster with them, but I'm going to go ahead and use the division rule, where I take the top exponent minus the bottom exponent, because that will give me negative 3 minus negative 5. And if you're very, very good with this, you remember that minus a negative is the same thing as adding a positive. So negative 3 plus 5. Well, negative 3 plus 5 is just positive. And so that became a lot simpler than it had to be. The reason this is in the steps of putting it all together is some people will first fix the negative exponents. They say, hey, this 5 to the negative fifth, needs to go up top. This 5 to the negative third needs to go to the bottom. And then they'll combine it. They'll use two different exponent rules and end up with the same answer. Okay, it doesn't matter what order you work as long as you're doing correct exponent rules and you stop whenever you have all these three things achieved. Let's do another example. Let's see, oh, those are simple. We've already done examples just like those. Let's jump to one more useful. 2x to the fifth divided by x squared, and it's going to be raised to the third power. Okay, well this is a nice example. Any order of these things works. Some people will combine like bases first, then do the power to a power rule. Some people will start with the power to a power rule and then combine like bases. But guess what? In the end, you get the same answer. I'm going to go ahead, because I see that the exponent on the top is bigger than the bottom, I'm going to go ahead and do the combine the like bases. So I have this 2's just there for the ride, x to the fifth divided by x squared. And the rule says to subtract 5 minus 2, which is 3. And I haven't done anything with this 3 on the outside yet. I just combined like bases. Okay, well, now I have this exponent on the outside. I need to remember that this 2 has an exponent of 1, but I should be able to use my power to a power rule. 2 to the 1 times 3 is 3, and x to the 3 times 3 is 9. Okay, so that took two different exponent rules in 2 steps, but that really wasn't that difficult or nasty. We can expand to doing some kind of larger things. What if I take two terms? Let's take the term 4x squared y squared, and let's multiply it by another term, negative 2x y to the third. Oh, well, this isn't too difficult. This is also really easy. I'm just multiplying two terms. When I'm multiplying them, 4 and negative 2 are just plain numbers. I can multiply those. 4 and negative 2 should multiply together to give me negative 8. Nice. And then I'm multiplying x squared and x. There's no exponent here. Oh, it's understood to be 1. X squared and x to the first. I know if I'm multiplying like basis, I can combine those together and add their exponents, x to the third. And then I have y squared times y to the third. I know I can combine those into a single y term, or y base, and add the exponents. 2 plus 3 is 5. So just using my exponent rules, I combined like bases and I multiplied the plain numbers out front, and I got a lot simpler of an expression. And let's see, I've combined all like bases. There was no parentheses really to worry about because once I multiplied they were gone, and there's no negative exponents. Okay, that's pretty simple. Maybe one more example about the biggest, baddest problem we can give you. Maybe what I'll do is scroll down and get some more paper to have plenty of space for this one. It shouldn't take that much space, but let's say I go with something like this. Let's say I do, what do I want to do? 28 x y to the negative 5, that's a negative sign, divided by 7 x to the negative 3 y to the 5. And so I can go ahead and look at this and say, oh, I got this big division with plain numbers. I know 28 divided by 7. If I have two numbers that can divide or multiply, just like in the last problem, let's go ahead and take care of that. 28 divided by 7 is 4. Okay. So if there are plain numbers that we can handle the operation with, go ahead and do it just to get them kind of out of the way. All right, now looking at the rest of this x doesn't have an exponent, so I can put a 1 there. Now it looks like I'm just going to combine like bases, and this is that division rule. I'm going to bring, let's see, 1 minus negative 3 would be 4. Negative 5 minus 5 would be negative 10. So I moved everything together. I combined these like bases with a division rule. I combined those like bases. I'm not finished yet because I can't stop with a negative exponent. So this gets to stay because it has a positive exponent. This gets to stay because it has a positive exponent. This y to the negative 10 needs to move. Now because it is on the top of the fraction, the only other place to put it's on the bottom. And when you move a base and its exponent up or down, it turns on or off the negative sign. So there. We've fixed that. Nice. Let's see, I'm trying to think. I might want to do one more example just to make sure we kind of feel pretty good. One last example. I know I said that was the last one, but one last one. Let's go with, what do I want to do? Let's go with something like this. 2x to the negative 2 divided by y to the third, all raised to the negative 2 power. So a lot of people will take time to do different exponent rules. Some people will deal with all the negatives. Some people will start with multiplying. I suggest I would start with this power to a power rule. Now this 2 needs an exponent on it, and so every exponent in here is going to get multiplied by negative 2. So that would give me 2 to the negative 2. Negative 2 times negative 2x to the positive 4. And y to the 3 times negative 2, that'd be y to the negative 6. Okay, so all I have left now is to fix negative exponents. This 2 squared has a negative exponent, so it needs to move. It was in the top of the fraction, so it's going to move to the bottom of the fraction and become a positive squared. This y to the negative 6 needs to move. It was in the bottom. It's going to come up top and become y to the positive 6. And this x to the positive 4 already was positive, so it doesn't move. And so he gets to stay put. This one moves down. This one moves up. And there's our final answer. So, take some time if you need to slow down or pause or watch that and to be able to put together these exponent rules. Order does not matter. You could have worked this in 7 different ways probably. But just know that you're just going until you've combined all like terms, you've used up all your parentheses, and there are no negative exponents. Okay? All right, see you next time.